Hello everybody, welcome back. So as you can see, I've prepared, a slight modification of the problem that we just did and a new one. I'm not going to go through the entire F equals ma analysis where you draw the free body diagram, you write the F equals ma equations, you think carefully about your coordinate system, then you do the constraint equation and go through, a little bit of algebra. I'm not going to do all of that. Instead, because a lot of the kind of new stuff in this particular genre of problem is the constraint equation, I just want to go through, two quick examples about how we would handle, these two systems. So again, the name of the game is consistency. The way in which you measure your blocks is determined by the coordinate system that you choose to use. And in this case, let's do a slight variation of what we did in the previous one. So let's say that I think that this should be my I-hat direction for block number 1. Correspondingly, let me still choose J as vertically upward. And let's say that for block number 2, that J is still vertically downward. Now, the kind of switch is that now that this I-hat direction is directed downward, that needs to change how we describe the position of these blocks. And in particular, what we need to do is, remember, you need to measure the position of the blocks in the same direction as you choose your unit vectors. So in this case, rather than measuring from the bottom of the ramp and going upward, like we did in the previous problem, because my I direction is now downward, that's a choice that I, the problem solver, has made. Now I need to measure the position of this block, starting at the pulley and going in the same direction as my I-hat direction. Similarly, I also need to measure the position of this block number 2, also in the downward direction. Now, remember, the name of the game for these kind of constraint equations is you want to equip yourself with an expression for the length of the rope in terms of known variables and some quantities that you might have to define in the problem. So in this case, let's go kind of segment by segment in the rope. Let me think about this first segment between block number 1 and the pulley. Well, that length is just what we're calling x1. Now, if I want to do another segment, let's think about this one here, the one connecting the two pulleys. You might be tempted to say that's, y2. And if you want to be precise about it, what you can do is, remember, you're allowed to define constant lengths in the problem. So I could kind of facilitate this process, and I could say, well, I could call this distance between, this kind of pulley and the ceiling, I could just call that some constant distance, d1. In that case, this length of rope between the two pulleys would therefore be y2 minus that constant length, d1. Now, in this case, one thing I do want to point out is that there are two lengths, or there are two ropes in the problem. That means you might think that there have to be two forces of tension. But in this case, what I want to do is I want to point out that the distance between this bottom pulley and block number 2 is always going to stay constant. In particular, what that means is that they have to have the same acceleration. So we can treat this particular cluster of objects as kind of thinking about it as just m2. Again, we can do that because the length between them is constant. That means they always have to have the same acceleration. So that takes care of this length here in the problem. And now we want to move on to what's the other kind of length, the one that's connecting the pulley to the ceiling. That again is just y2. Or if you again wanted to be very precise about it, you could define the distance between this pulley and block number 2 as some constant length d2, and that would just be y2 minus d2 if you really wanted to be particular about how you're measuring. But again, we have this equation for the length of the rope. To get the constraint equation, we take a time derivative, or two time derivatives. So the left-hand side goes to 0. And what we have is x double dot 1 plus y double dot 2 plus y double dot 2 is equal to 0. I get two pairs of y double dot because, again, this thing kind of has a wraparound to it. So my constraint equation reads that x double dot 1 is equal to minus 2 y double dot 2. Again, the thing you want to pay attention to with these constraint equations, you write them down, you go through the algebra, and you want to make sure that they make sense. So let's pay careful attention to this negative sign. You always want to make sure, kind of go through the hypothetical in your head and make sure that it kind of is physically reasonable. So what this says, I translate that negative sign into words, this says that if x1 moves in the positive direction, y moves twice that amount in the negative direction. We want to ask ourselves, does that make sense? Oh wait, I'm sorry. I misspoke a little bit. In particular, let me kind of rearrange this a little bit. Like so. Just to facilitate our discussion, what this means in words is if x moves in the positive direction, y will move in the negative direction by half that amount. Let's make sure that makes sense. What is the positive direction for x1? Positive means x1 moves down the ramp. Does that induce negative motion in y2? Negative is opposite the direction of our j. That's upward. So the signs make sense. If x1 moves downward in its positive direction, y2 moves in its negative direction, which is upward. The signs make sense. Now, the factor of 1/2 comes from the wraparound. If I think about displacing this block number 1 by some small amount, that block number 2, that displacement, is kind of cut in half. Half of it goes to one side of the pulley, the other half goes on the other side of the pulley. So both the factor of 1/2 and the signs, positive and negative, make sense. That's something you always want to check at the end of every kind of constraint equation. And now let's talk about how would you approach a more complicated system like this. So this is where, again, I preach the gospel that you have freedom of choice with the coordinate system as long as you stay consistent. So I look at this problem as somebody who's done a lot of pulley problems, and I say, well, the kind of path of least resistance to doing this particular problem is, I would say, I can choose this to be x1. That way I know that this segment of rope is just x1. Correspondingly, I could measure from the pulley going downward, I could measure that as y2. That way, this length and this length would essentially just be y2. And again, the path of least resistance is, I would call this the position x3. Now, we're doing something a little bit in reverse. Rather than looking at the coordinate system first and then deciding how we're going to measure, for a problem like this, it kind of is a little bit easier to measure first and then choose your coordinate system accordingly. This is that self-consistency that I'm talking about. So remember, our unit vectors have to be in the same direction as the way that we're measuring. This means that what is the I direction for block number 1? That needs to be 2 in this direction. Similarly, I'm measuring the position of block number 2 going from the pulley and moving downward. That means that what is the j direction for block number 2? It has to be downward. And similarly, what is the I direction for block number 3? It has to go in the same direction that I'm measuring that position. So this case, remember that the choice you make when you measure has to be the choice you make when you do your coordinate system. That has to be the choice you make when you do your F equals ma equations with the positive and the negative sign. And that has to be the choice you make when you end up getting your constraint equation. So this choice of signs is something that you have to stick with at 4 different points in the problem. If you look at your final answer, or if you look at the final answer of your friend and you have a similar situation that we described last time, where for a finite combination of non-zero masses, your denominator is equal to 0, and therefore there's a non-zero probability that a pulley with infinite acceleration will come crashing through the window, that you have to look at those 4 steps and analyze, did I stay consistent with my coordinate system? So let's talk about this particular constraint equation. Again, the name of the game, I want an expression for the length of the rope. I've done my measuring to make this a very painless process. In this case, that segment of rope is x1. I go down to the pulley and then I go back up. In each case, that gives me 2 parts of y2, and I go from this pulley and I measure till I get to block number 3. This is x3. Therefore, if I want to do the constraint equation, I just add a couple of dots above each variable. And remember, this is non-stretchy rope. Therefore, when I do the time derivative, this should be equal to 0. Does this make sense? Well, let's imagine that for this particular case that we're going to analyze, let's say that x1 is a stationary object. If we analyze just this particular case here, if I kind of draw what this system will look like, that means that, well, block number 1 is essentially just a wall. I have my pulley that goes up and around. And does it make sense? So, do we anticipate? Well, if block number 3 moves in its positive direction, again, let me do the same kind of rearrangement we did last time. If I read this equation, it says y double dot 2 is equal to minus x double dot 3 divided by 2. We do the same interpretation. I highlight the negative sign because that's the important part, is if x3 undergoes a positive displacement, does y double dot 2 move in its negative direction? Let's think, does that make sense? If I take this block, I move it in its positive direction, which under the assumption that I made, that means that this block is moving this way. Does that correspondingly induce a displacement in the direction opposite my j direction? That's the negative sign. Indeed, it does. So the signs work out, and again, this factor of 1/2 comes from the wraparound of the pulley. So thematically, that's something you'll see kind of on a lot of problems that have the wraparound. But I just wanted to walk you through 2 kind of constraint equation problems. This is the, I know for a lot of you, it's the part of the problem solving process that's new, but hopefully, kind of gain some more experience kind of watching this particular video. And I will see you next time.